Greetings to everyone. My name is Himanshi. I'm a BTech third year student at Department of Physics, IIT Roorkee. Today I'm going to present about digital signal processing as a part of my coursework. So, giving an outline, we're going to talk about signals and signal processing. What is digital signal processing, signal sampling? How does DSP work? We're going to look at block diagram of a DSP system, its implementation, and its applications. Starting with what are signals. A signal refers to any continuous function or one or more variables such as time, space, frequency, etc. For example, velocity of a vehicle, light intensity of an image, temperature, pressure inside a system. Signal processing and its types. Signal processing refers to the science of analyzing time-varying physical process. There are two types of signal processing: analog signal processing and digital signal processing, which we are going to look at later on. Analog signal processing is used to describe a waveform that is continuous in time and can take continuous range of amplitude values. It will be more correct to say continuous signal processing. Now, what is digital signal processing? It is the use of digital processing, such as by computers or more specialized digital signal processors, to perform a wide variety of signal processing operations. Digital signal processed in this manner are a sequence of numbers that represent samples of a continuous variable in domains such as time, space, or frequency. In digital electronics, a digital signal is represented as a pulse train, which is typically generated by switching of a transistor. So, how does this work? Signals need to be processed so that the information that they contain can be displayed, analyzed, or converted to another type of signal that may be of use. In the real world, analog products detect signals such as sound, light, temperature, or pressure and manipulate them. Converters such as analog to digital converter then take the real world signal and turn it into a digital format of ones and zeros. From here, the DSP system takes over by capturing the digitized information and processing it. It then feeds the digitized information back for use in the real world. It does this in one of the two ways, either digitally or in analog format by going through digital to analog converter. All of this occurs at very high speeds in a very low time. Signal sampling. To digitally analyze and manipulate an analog signal, it must be digitized with an analog to digital converter. Sampling is usually carried out in two stages: discretization and quantization. Discretization means that the signal is divided into equal intervals of time, and each interval is represented by a single measurement of amplitude. Quantization means each amplitude measurement is approximated by a value from a finite set. Theoretical DSP analyses and derivations are typically performed on discrete time signal models with no amplitude inaccuracies such as quantization error created by the abstract process of sampling. In the image, we can see a continuous time signal, which is then a sampled signal. So, to illustrate this concept, the diagram shows how a DSP is used in an MP3 audio player. During the recording phase, analog audio is an input through a receiver or the other source. This analog signal is then converted to a digital signal by an analog to digital converter and passed to the DSP. The DSP performs the MP3 encoding and saves the file to the memory. During the playback phase, the file is taken from the memory, decoded by the DSP, and then converted back to an analog signal through a DAC, so it can be output through the speaker system. In the more complex example, the DSP would perform other functions such as volume control, equalization, and user interface. Here we can see a block diagram of a DSP system. The first step is to get an electrical signal. The transducer, in our case, which is a microphone, converts sound into an electrical signal. We can use any transducer depending upon the case. Once we have the analog signal, we pass it through an operational amplifier to condition the analog signal. Basically, we amplify the signal or limit it to protect the next stages. The anti-aliasing filter is an essential step in the conversion of analog to a digital signal. It is a low-pass filter, meaning it allows frequencies up to a certain threshold to pass. It attenuates all frequencies above this threshold. These unwanted frequencies make it difficult to sample an analog signal. The next stage is a simple analog to digital converter ADC. This unit takes in analog signals and outputs a stream of binary digits. The heart of the system is a digital signal processor, which we call as DSP. These days, we use CMOS chips to make digital signal processors. In fact, modern processors like Cortex M4 have DSP units built in inside. These processors have high speed, high data throughputs, and dedicated instruction sets. The next stages are sort of opposite of the stages preceding the digital signal processors. The DAC does what its name implies. It converts the digital to analog signal. The smoothing filter is another low-pass filter that smoothes the output by removing unwanted high-frequency components. The last is just an amplifier. The output is a speaker in our case. We can use anything according to our requirements. What is inside a DSP? It contains program memory, which stores the programs the DSP will use to process data, data memory, which stores the information which is to be processed, a computer engine which performs the math of processing, accessing the program from program memory and data from the data memory, an input and output which serves as a range of functions to connect to the outside world. Domain. In DSP, we usually study digital signals in one of the following domains: time domain, spatial domain, or frequency domain, and wavelet domains. We choose a domain in which to process a signal by making an informed assumption as to which domain best represents the essential characteristics of the signal and processing to be applied to it. The sequence of samples from a measuring device produces a temporal domain representation, whereas a discrete Fourier transform produces the frequency domain representation. Time and space domains. Time domain refers to the analysis of signals with respect to time. Similarly, space domain refers to the analysis of signals with respect to position, for example, a pixel location in case of image processing. The most common processing approach in the time or space domain is enhancement of the input signal through a method called filtering. Digital filtering generally consists of some linear transformation of a number of surrounding samples around the current sample of the input or the output signal. The surrounding samples may be identified with respect to time or space. The output of a linear digital filter to any given input may be calculated by convolving the input signal with an impulse response. Frequency domain. Signals are converted from time or space domain to frequency domain through a use of Fourier transform. The Fourier transform converts the time or space information to a magnitude and phase component of each frequency. With some applications, how the phase varies with frequency can be a significant consideration. Where phase is unimportant, often the Fourier transform is converted to the power spectrum, which is the magnitude of each frequency component squared. The most common purpose of analysis of signals in frequency domain is analysis of signal properties. Next, coming on to wavelets. In numerical analysis and functional analysis, a discrete wavelet transform is any wavelet transform for which the wavelets are discretely sampled. As with other wavelet transforms, a key advantage it has over Fourier transform is temporal resolution. It captures both frequency and location information. The accuracy of joint time frequency resolution is limited by the uncertainty principle of time frequency. Here we can see an example of a 2D discrete wavelet transform that is used in this image. The original image is high-pass filtered, yielding the three large images, each describing the local changes in brightness in the original image. It is then low-pass filtered and downscaled, yielding an approximation image. This image is high-pass filtered to produce the three smaller detail images, and low-pass filtered to produce the final approximation image in the upper left. Now, implementation of DSP. The DSP algorithms may be run on general-purpose computers and digital signal processors. The DSP algorithms are implemented on built-in hardware applications, specific integrated circuits. For systems that do not have a real-time computing requirement and the signal data exists in data files, processing may be done economically with a great general-purpose computer. An example of such application is processing digital photographs with software such as Photoshop. When the application requirement is real time. DSP is often implemented using specialized or digital processors or microprocessors, sometimes using multiple processors or multiple processing cores. Coming on to the applications, DSP is used in speech recognition and processing. It can be used in image enhancement and image processing. It is used in medicines, audio compression and audio and video compression, computer graphics, economic forecasting, and many more. Here we can see another implementation and application, that is noise removal from speech and noise removal from image on the right side. Thank you.